Hello, it's Keith here, and this is lesson 4 of the x86 assembly programming tutorials. Now, we've covered our conditions and flags last time, and we've looked at mathematics and addressing modes in the past, but we skipped something really important, and I think something that is kind of fun if you're into your programming is the important thing known as the stack. Now, the stack isn't something I'd ever really had to worry about when I was programming in BASIC and even programming in C. In a lot of cases, I hadn't had to use it, but it's a very important concept when it comes to assembly. Now, in assembly, of course, we've got a limited number of registers, and we will be doing various mathematical operations with values, and sometimes we'll need to back up a value for later, and we'll need to do another few operations and then get that value back. Now, one option would be to store that into RAM in a fixed address location, which we specify with a label or something, and of course that would be an option, but it's not very flexible, and we wouldn't want to do that for every single time. We want to just temporarily quickly store a number while we're doing another operation, and that's where the stack comes in. Now, what I suggest you do is you think of the stack like your in tray in an office. Now, if you think of an in tray, you might get lots of jobs and you can't deal with them all at once. So you'll put a job in the in tray, and then you'll put another job on top of it in the in tray. And when you come to take things out of the in tray, I want you to think of it like you can only ever take the top item off the in tray. And so you put them in an order, you take them off in the reverse order. And this is known as a last in, first out stack, because the in tray in my example is the way that the stack works in the x86 processor. Now, the stack in the x86 is effectively a location in memory, and whenever we store new data, the address pointer is actually moving down, going up into memory towards 0, and new data will be stored at progressively lower locations, and then when we remove that data, it's taken back off in the reverse order. And this is very good for temporary storage, because we might want to store 3 values for a moment while we do another calculation, then get those 3 values back. Now, if we're running within a subroutine, our parent routine might have stored some variables as well, so the fact we get the variables back in the reverse order till we put them on is very convenient for our programming, and we're going to see that in action in today's example. Now, the concept of stacks is very important. I don't want you to worry if you don't understand them at this point, because we've only just got into it. But by the end of this lesson, hopefully you will have a reasonable understanding of them, and you will be able to sort of progress if you need a little bit more help. Try some of the examples out until you get them clear in your head, because they really are essential to assembly programming, because we are so limited with our number of registers, and there will be so many times that we need to store things temporarily. And we'll learn that stacks actually take an essential part in subroutines themselves, and we'll learn that in just a moment. So let's go over today's example and let's learn about stacks. Okay, so here is the code today. So this is the lesson 4 assembly file, and we've got a variety of tests, and we're going to go through them one by one, and we're going to learn from each example something about the stack. Now, today's code has a lot of stuff that we're not going to go into. Look at all this horrible code, very complex, and I had to do it to allow us to see the state of the stacks on screen. I don't want you to worry about this. It's just stuff that's going to help show things to the screen. It's not actually part of the tutorial, what we're learning today. But if you've got your own assembler debugger, you might not need them. You might have other things that can monitor the stack, but these are just going to show the state of the stack and the registers to the screen for us, as well as I can with these tutorials. So we're only going to cover the code that these labels here jump to, and these are the functions like this. These are code that is provided as part of my tutorials to just show the state of the stack and the state of the registers. Okay, so let's see this first stack test, which is a very simple example of the stack. And let's fire it up just here. Okay, so if I just pop this on, lock it onto the top of the screen, get it up just here. So here's our first stack test example. Now, the commands for putting things onto the stack and taking them off are push and pop. Now, we push something onto the stack and it pops back off when we want it. So it's kind of a spring-loaded stack, I guess, but maybe like one of those coin holders that you push coins in and they're held in with a spring. I mean, maybe that would be the way to think of it. But anyway, we push a register on. So in this case, we're pushing AX onto the stack, and here we're popping AX off the stack. Now, on the x86, the stack pointer is SP, and we will see that in some cases, and the stack pointer will be initialized when our program starts, and every time we push onto the stack, it will actually go down, because the stack goes down in memory on the x86. But we don't need to worry about that in this case. So what are we doing here? Well, we're loading AX with a value here, 1, 2, 3, 4. We're then just using this monitor to show the value AX, and you can see it just here, 1, 2, 3, 4. And then we're pushing it onto the stack. and we're loading another value into AX, and this is simulating some more mathematical operations. Maybe we need AX for something else for a while. So we've loaded 5678, you can see here. And we want then to get back the value AX had before we did that. And so we're popping AX back off the stack. And this effectively restores the value AX had when the push command occurred. And you can see 1234 has been restored just here. Now, in this case, you can see there's no other command that would load 1234 here, and it's that pop command that's done it. Now, the contents of the stack have actually been shown just here. And you can see now here in little endian, so the bytes reversed, 1, 2, 3, 4 at the top of the stack. Because remember, the stack moves down, so it moves in this direction in memory in this display here. So you can see here that 1, 2, 3, 4 was pushed on by this command just here. And I can just prove that to you. What happens if we just put another push command here, and we'll copy another pop command here, because we want to always match our commands. We want to make sure we take off as much as we put on. If you've got an office in tray and you're putting more in than you're taking out, sooner or later you're going to have a bad day. And on the 8086 in the same way, if you never take the stuff out you put in, you're going to have a bad day. So you can see here now there's two 1, 2, 3, 4s on the stack there. So that's how we can push values onto the stack and take them off to back up and restore AX. And of course, there's no reason we need to just use AX. We can use pretty much anything. We can use BX instead. Let's just try that. Now, it will work, but we won't be able to view it because do we have them do monitor BX? We probably have one. Hang on a minute. Let's just do a proper job here. Yes, we've got a command to see BX. So there we go. You can see it did work. So we are able to back up and restore a value with any register here just fine. So that's our first example, and hopefully that's not too concerning for you. Now, I don't know what stage you're at with your programming, but you might not immediately think why you would need to do that, but you will find quite often maybe you want to do some addition and subtraction and then use that value with your original value in AX, and you need registers to do those kind of mathematical operations. So just remember these kind of commands, these push and pops, and later on you'll quickly come across places where they're really helpful to you. Okay, so in that example we just used a single push of AX, or we doubled it up, but we're just pushing one register, and we can of course push multiple registers, but in all the cases here we're just going to look at AX on its own just to make a point. Now, because every time we push we're moving up the stack, and every time we pop we're moving down, we can nest these commands. So there may be cases where we back up AX, do some more work, and then we want to back up AX a second time and restore in the reverse order. And you can see this here. I've put these tabs in so you can clearly see the matching pushes and pops. So this push and this pop are aligned, this push and this pop are aligned, this push and this pop are aligned. And so every time we pop here, we will get the value that was pushed on in reverse order. So we'll just fire this up and we'll see it quite clearly, I think. Okay, so here's this example. So we've loaded 1, 2, 3, 4 here, and we've pushed it onto the stack. And you can see here, 1, 2, 3, 4. Now, because the stack moves down, when we load 5, 6, 7, 8 and push that onto the stack, you can see 5, 6, 7, 8. You can, again, in reverse little endian order, so 7, 8, 5, 6 is 5, 6, 7, 8 pushed onto the stack. And then here we're loading 9ABC here and pushing that onto the stack. 9ABC. Now, the final value we load into AX here is DEF0 here. Now, that never gets loaded onto the stack, but you can see when we're doing these do monitor AXs here, 1, 2, 3, 4, 5, 6, 7, 8, 9ABC, DEF0. So this here is being done by this section of the code here. Now, we've loaded all these values and pushed them all onto the stack, and then when it comes to popping them off, we are popping them off in reverse order. So we pop off something into AX and we get 9ABC, this value, and at this value here, and then at this point the stack pointer would have moved to here. So when we pop off again, we then get 5, 6, 7, 8, and the stack pointer will have moved to here. You see that 5, 6, 7, 8 there, and the final pop is 1, 2, 3, 4, and then the stack pointer would be here. Now, there's something important to notice here. If I take these tabs out, these tabs are purely visual. This is going to have the exact same function. I just put the tabs in because it makes it clear and it avoids making mistakes, because we do need to match our pushes and pops here. So you can see here, code's worked exactly the same without those tabs. The tabs don't matter, but matching the pushes and pops do. If I put 2 pushes in here, well, now you can see we've put 2 5 6 7 8s in here, and 1 2 3 4 never got restored. And even worse than that, if our code continued and we never got rid of that extra pushed on item, we would quite probably come up with a crash at some point. So it's important to leave things as you found them, so to speak. You know, a bit of a metaphor there, but make sure you tidy up your mess once you're finished, I suppose, would be what we're saying. So yeah, we're pushing on values and popping them off, and we do have to do them in the same order. Now, it's not easily possible. I'm not going to call it impossible, but it's not easily possible to get back an old value here. So for example, if we had pushed on BX just here, now if we wanted here to get back that pushed on value BX, there are ways we can do it, but when we pop, if we can't do pop BX here and get the BX we pushed on here, we would actually pop off the AX we pushed on here. When we push and pop onto the stack, the commands don't know what register was pushed on, whether it was AX, BX, CX or DX. They just know the value of the register, and this does actually allow us in some cases to do some quite clever tricks. So we can do, for example, if we load BX here and then do push BX and then pop AX and then view AX here, we'll just change this to FFEE, just so we've got a new value that we haven't seen before. Well, we've loaded BX with FFEE here, pushed it onto the stack as BX, popped it off as AX, and you can see that now AX contains the value FFEE here. So, as I say, the point is the value going on the stack, not the named register, not AX, BX, CX, DX. It's the value in AX, the value in BX, and the value in CX. And so again, if we want them to come back into the same register we pushed them on as, we need to make sure we match them, otherwise something strange will probably happen. So that's how we can use the stack to store values temporarily while our code is running. But the stack has a very important function when it comes to the processor and subroutines. Now, if you think of a subroutine, whenever we call a subroutine, the processor is going to need to remember what actually started the subroutine, so that when it returns and the program counter, the currently running command, needs to reset to point to the command that it needs to run next, it needs to remember that somewhere. Now, to a great extent, the 8086 doesn't have any secret resources it's not told us about. It's not got some massive extra stack of registers that it can use to remember things. I'm just giving the clue away. It remembers the return addresses on the stack itself. So when we do a call, the processor is effectively pushing the return address onto the stack. And when we do a return, it's effectively popping that address into the program counter and then continuing our code. And that's why it's so essentially important that we restore the stack and clear up our mess when our subroutine finishes, because otherwise that return address might not be where it's supposed to be, and we might end up running code that isn't supposed to be code at all. So let's have a look at nested calls here. So we've got this command here, do monitor IP. IP is the program counter on the 8086. We've got do monitor AXBX, which will show the AX and BS registers. And then we're going to do a call to here. And we're going to see what actually goes on within our processor using these little simple debugging tools. Okay, so let's just force this to the top of the screen here, and let's just have a look at our code. So here we're loading in AX and BX with 0, so just a starting point here. And we are showing the current running code 0315 here. So that will be this piece of code here, the memory address of the running code, if you will. Now, what are we doing here? Well, now we are going to call test nested call 1, which is this code just here. So what we're doing next is we're pushing BX onto the stack here, and then we're calling nested call 2. Now, nested call 2 is adding 1 to AX and BX and showing the results, and you can see those results just here. Now, you'll notice the IP, the program counter, has actually changed here. It's gone a little bit further, and that's because we were running this line of code, and we're now running this line of code just here, so it's obviously a little bit further down. And then what we're doing here is we're running nested call 2 once again. And then nested call 2, once it's shown the registers to the screen, is returning, and so this line of code will be running next. what we're doing then is we're running the code again, adding another 1 to AX and BX, and then we're returning. So this will then run this bit of code. This bit of code is then restoring BX, and then it's adding 10 to both AX and BX, and then it's returning, and that's going to return to just here. Now, what actually happened to our registers? Well, let's take a look. So you can see the states of the registers just here, and you can see the BX now contains just 10. You will also see that the stack contains a variety of values here, and let's take a look at them, shall we? Well, why does BX contain 10 when AX contain 12? Well, that's because of the push and the pop here. You see the two calls to nested call 2 here both added 1 to AX and BX, but once the second one had run, BX was restored from the stack and got back its original value of 0, and then only the add 10 that occurred here affected BX, but AX was unchanged, so AX retained both of the additions from these two and also the addition from here. Now you can see the 00 here, and that is the 00 pushed on by BX here. Now I'll just prove that to you if I just change this to 55 here. This 5500 here, that is BX being pushed onto the stack, and that's being done by nested call 1 here. But you can see there's a value 0356 before that push onto the stack, and there's also another value 03C7 after the nested call here being pushed onto the stack. Well, what has pushed those values onto the stack, and what are they? Well, maybe you understand it from the clue I gave earlier, but we'll explain it now. Now let's take a look at this value here, 0356. What is that value? Well, if you look, we did a call to nested call 1 here, and just afterwards we did a showing of monitor IP here. Now let's look for that in this routine here. Well, you can see 0363 here is the returning address after our program ran, and just before 0315 was the address just here before our call run, and 0356 is effectively the first line of this command just here. Now it doesn't quite match because these are actually macros, and we'll cover that in a moment, but these have actually got a lot of other commands in them, so the program counter has shifted along a bit, but this is effectively here 0356 is the return address for after this line has run. You see the call has pushed the return address onto the stack here, and then this call here has also pushed the return address 03C7 onto the stack, and you can tell that because when we did do monitor IP here, you could see 03C2 just a few bytes before. So every time we do a call, an address is pushed onto the stack. Now we did two calls to nested call 2, but they would have both written to this same address because after the return, the stack pointer moves back up. Now the stack pointer at the point we showed this stack, of course, will have moved back here, but even though the stack pointer moves, the old values are never zeroed, they're only overwritten if we do another push. So both of these calls will have written to this area here, and that's why we only see this value once, not twice. So as I say, the important thing to take away from this, because I know it's confusing, but the important thing to understand is when we do a call, we're pushing a return address onto the stack. When we do a return, we're popping the program counter off the stack, the IP off the stack. And the only important thing to understand about this is be very careful about pushing and popping. Now, in this case, we've pushed onto the stack here and popped off the stack here. Well, let's put a push AX on the stack here and a pop AX here. Well, that's going to be just fine. There's no problems at all with doing that. Our AX value now doesn't really change because we are restoring it after adding to it. So you can see that all of these ones are immediately lost as soon as the pop occurs. But what happens if we do this? Mayhem happens. Well, what happened there? Well, we pushed onto the stack, but we didn't clear up our mess. So when we returned, the value we pushed onto the stack was treated as the return address, and the program counter ran goodness knows what, and goodness knows what made a right mess of our screen. So that's why we need to pop off everything we push on. And in the same way, we need to be careful about popping off things we didn't push on, because in this case, if I run this, well, the program has stopped halfway through and a mess is occurring. What happened there? Well, when we popped a value we didn't push on here, rather than getting any previous value of AX, we actually got the return address of this line here. And that means when the return happened, there was nothing left to take. So we've again made a mess. Now, there are some tricks you can do with this. You can get return addresses and things. If you've got clever ideas, you can do them. Now, what we can actually do is we can be clever and do things like this. Now, in this case, it's actually worked fine. What we did is we popped the return address off the stack and immediately pushed it back on. So we didn't damage it. It's still there, it's fine. So that hasn't caused any problem. But we do have to make sure if we mess with that return address, and as I say, you don't worry about it if you don't understand this, but if you mess with the return address, in this case we added 1 to it, so when we put the return address back on the stack, it ran the wrong byte of code, probably misunderstood a bunch of commands, and a nasty mess has happened. So the best thing to do as a beginner, make sure that your subroutines end with the stack in the same state as it started, because if it doesn't, you're going to make a mess. When you get more skilled, when you get more confident, and when you start to have your own cunning ideas of what you might want to do, you might have some tricks that you want to do, and this might be a great way of doing them. But in the early days, keep it safe. Just make sure that the stack ends up in the same state as it started, and you'll be just fine. Okay, now this is a little bit more tricky, but I think it's important to discuss because it's a feature of the x86. Now, when it comes to the stack, there is sometimes you will see, particularly with firmware functions, you might pass parameters rather than in registers. You might push them onto the stack before running a subroutine, and the subroutine, or the operating system call, will get those values off the stack and it will do some work with them. And this is very handy for passing things when we don't have enough registers, or we need too much data, or we need the registers for other things. So we're going to see this in action now, because the x86 actually has the ability for the returner command to actually deal with removing some of these parameters. And also we have the ability to move the stack pointer into another register, in this case SI, and then be able to read from the offset and get those values directly into other registers. And that's what we're going to do just here. Okay, so let's fire this example up here now and let's see what happens. Okay, so what happened here, first we've just shown the current state of our registers just here. You can see all of these here. And then what we're going to do is we're going to actually load in some values, and we're going to call our test routine here. So what we've done here is we've loaded AX with FEDC here and pushed that onto the stack, and then we've loaded AX again with BA98 here, and we've pushed that onto the stack. So these are two parameters for our test routine to grab hold of. And so you can see here, I mean, AX obviously contains the last one of these, and then it's called our subroutine just here. And this has loaded our stack pointer, which you can see just here, into SI, which you can see just here. And SI is the source index for strings, but we're just using it as an offset here. And then we're needing to specify the segment. We're specifying SS, which is the stack segment, because you see the address that in the 059C refers to here wouldn't be the same address that the IP program counter would probably be referring to as 059C. They might be different addresses. It just depends how things are set up. Now, in this case, they actually are the same, but you can't rely on that. So you do need to specify the stack segment. And we're loading from the stack segment the stack pointer +2, because remember the stack moves down every time things are added to it, and the first 2 bytes will be the return address that the call here will have put onto the stack. So we're loading the first parameter here into CX, and you can see on return here CX was BA98, so this value here. We then loaded DX with the next value +4 on the stack, and you can see DX is FEDC, and that's the second value that was pushed onto the stack in reverse order, of course, just here. Now, we were able to return just fine here, and when we returned, if you look, the stack pointer was 059C, and when it started, it was 059C. Now, the two values here were pushed onto the stack, but they've effectively disappeared. Now they've disappeared because this return has taken 4 bytes off the stack pointer as well as returning. So this has effectively absorbed these 4 here. Well, we can prove that if I change this and I change it to 0. Well, our programs run fine because the stack wasn't affected here, but when it's returned here, you can see here it's 0596 and here it was 059A. So the stack is now further down because there's still these 4 items waiting for something to take them away. And if nothing ever takes them away, that could cause a crash later on, either if we've got a return or if we keep doing this, keep putting things on to the stack and not taking them off, eventually that stack's going to run out of memory. So as I say, we could have got rid of these in another way. We could have had a bunch of pops here, or we could have added 4 to the stack pointer. But this ability to specify a number of bytes to remove from the stack on a return is a really easy way of taking things off the stack without adding extra commands. And it's something the 8086 has that you sort of look at the Z80 and thinking, oh, that's a fantastic option to have. So it's definitely worth bearing in mind for later on. It's not something you're going to need in the early days. It's just one for when you're getting cleverer and you're starting to write your own fairly advanced things. But it's important I covered it as part of an example on the stack because it's something that I found particularly exciting about the 8086, if you find stacks exciting, which actually I do. So there we go. Now, we've looked here at how to push regular registers onto the stack. We can push AX, BX, CX, DX, all of our segment pointers and things, but we can't push the flags. We have to do something special for the flags. We have push F, which is all one word, there's no space there, and pop F. And this will actually push the flags themselves onto the stack and pop them back. Now, as well as this, we're using 2 new commands here, which are a bit complex, but we needed to see them at this point. SAHF, store AH into the flags, and LAHF, load AH from the flags. And SAHF will load the top half of AX into the flags, and LAHF will load the top byte of AX from the flags. So these are allowing us to transfer part of the flags into our accumulator or from our accumulator. And we're using this here to clear quickly and show the contents of the flags. So let's just fire this up and let's see what happens in this example. Okay, so you can see our stack here is empty, and what we're doing here is we're pushing the flags onto the stack here, and we're just showing the contents of AX in all of these cases. So we loaded AX with all ones here, you can see that, and we then transferred that to the flags, and you can see all of the flags were set here. And then we loaded AX with 0, and we moved AH to the flags here, and you can see these flags were all cleared here. Now this I flag here wasn't changed because that is outside of the top byte of the flags. This isn't actually changing all the flags. These push and pops back up and restore all the flags, but the other one doesn't. So you can see here SAHF didn't change that I flag there, but when we pushed AX being 0, and then popped the flags, we effectively transferred all 0 bits into the flags, and you can see here all the flags have been cleared. Now, and then what we did is we popped the flags off the stack, getting these flags back here. And then what we did here is we loaded AH with the flags here, and you can see that the top byte here has been set to 06, which is these flags here. And then if we want to get all of the flags, what we can do is we can push the flags onto the stack, pop them back into AX, and you can see here that actually those flags were down here, and the entire flag register is this value just here. And you can see here during this entire procedure, the only value pushed onto the stack was 7206 here, and that, well, with the exception of this one just here, which was 0, but that is the value of the flags that we got here, which is represented partially in these letters just here. Now, again, this is kind of something pretty technical that you're not going to need in the early days, but there may be cases you need to do conditions and things, and you need to store those flags for later, and the push F and pop F functions will do that for you. Now, this SAHF and LAHF are possibly a little more tricky, but as I say, they're definitely commands that are worth you bearing in mind, and I think it was important to discuss them at this point, and it was also a good way of seeing them in action. Okay. Now that's all we're going to cover on the stack. We've gone through it a little bit fast. We're going to of course see the stack a lot of times in the future, so I don't think you need to panic too much if you're a little bit hazy on it at this moment. Download the code, maybe try it out, but you're going to see it so many times coming up that it's not necessarily something you need to sort of worry about if you're still confused by it. But what we're going to do now is we're just going to briefly discuss macros. Totally different subject, but there were a lot of macros in this code because I needed to be able to show the contents of the stack without a call, because a call changes the stack. I had to use a lot of macros, and so I think it's only fair we discuss them. A macro is where we define a set of commands within our assembler, and then we use the label for that macro, in this example macro 1, and our assembler will swap that reference of macro 1 with all the commands contained within that macro. And this allows us to do a set of commands without using a subroutine. The disadvantage is it takes a lot more memory because we're replacing, before the compilation, this label here with all of these commands. But there are advantages, and the advantage for me today was it didn't change the stack like a call would have, because the call would have pushed the return address onto the stack. So this simple example will replace macro 1 with all these commands here. Now macros can have parameters. So we've defined macro 2 here with parameter 1 and parameter 2 here, and the macro is just loading parameter 1 into AX and parameter 2 into BX and then showing them to the screen. And if we just fire this up here, you can see all that has happened. So our macro 1 here is effectively a command to show a set of registers to the screen. AX, BX, IP and SP, you can see it's done that just fine here. So it's a nice way of combining commands and not changing that stack pointer when we do it, because as I say, if we'd have called to do a command that had done these, the stack pointer would have gone down by 2 because of the return address being pushed onto the stack. Now we could have changed it, but as I say, there might be cases where it's more difficult. So that macro has done this first part, and then these two calls to macro 2 here are actually doing this one, and you can see AX and BX have been loaded with the parameters specified here. So you can see here that macro 1 in these two cases here will have been swapped out by all of these commands, which is why you can see it twice and why you can see AX and BX are changing according to their position in the code. And macro 2 has also run twice with two parameters that we specified here. And as I say, it's the assembler doing this, not the actual processor. So this is a way that you can sometimes make very large amounts of long code that's fast very quickly. And if you want to do a command 100 times, putting a loop in slows things down. But you can use macros to have a repeating section shown dozens and dozens of times without having dozens and dozens of copies in your code, and then you can just change it once and it will change in all places, because as I say, it's the assembler doing a sort of a text-based replacement of this before the assembly occurs. And it's certainly something you're going to need to know later. Again, I think it's not really related to stacks and not necessarily something you'll need today, but this source code was covered in macros, and I thought we have to discuss it sometime. I thought it was fairest to discuss it at the point where I needed it to actually do the tutorial, because if you download the tutorial and you see all these macros and you don't know what they are, not really very helpful for you. So there we go, the tricky concept of stacks. I hope you've found this interesting. I hope you've found it educational. Stacks are essential to all the processors we've been looking at today. The TMS 9900 doesn't have one, but basically everything else does. ARM, RISC-V, Z80, PDP-11 really are all very much oriented around stacks. So as I say, it might not be something you're familiar with, but it's something that I think it's essential you learn. But don't be too worried if you're still struggling with it a little bit, because as I say, you'll come across it and you will start to get more of an understanding of it as you write code and realize why you need it. Anyway, that's all we're going to be covering today. Hope you've enjoyed it. I hope you found it interesting. If you have, please like and subscribe. I'd just like to point out I have a new URL for my website. It's the same website. I've just got some easier to remember URLs. So you can now go to learnasm.net or assemblytutorial.com if you prefer, and they will bring up a nice big list of all the processes I cover in my tutorials. I also have a forum. It's at chibiakimas.com/forum, or there's a link at the learnasm.net to it. If you want to chat about assembly programming or just chat about retro in general, please join along. Please have a chat and ask your questions, give your suggestions. If you've got better ideas of things I could have done better, please let me know, because it's all about helping others learn. So if I'm not teaching it in the right way and you know a better way, please share it with the rest of us. Anyway, whatever you do, I hope you enjoy programming. I hope you enjoy the 8086 and assembly in general. Thanks for watching today, and goodbye.